السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا. كملين معاكم اليوم إن شاء الله في بارت الهيت ترانسفير، ووصلنا لهذا السلايد convection. زي ما شفنا المرة الماضية الكونفكشن هو النوع الثاني من أنواع انتقال الحرارة. So the heat transfer happens through conduction, convection and radiation. Okay. So here we have a question. What happens طبعا of course this question we ask it in order to know the mechanism of heat transfer through convection. So in order to understand it, let us do this experiment together and ask this question. Okay, as you can see here we have convector or radiator. Okay, so this type of devices they used it to in the winter season. Okay, so here there is, maybe this is the inlet. Okay, so here we have water inlet. Okay, very hot water, and here we have the exit. Okay, and heat transfer. But how? Let's see. What happens to the particles in a liquid or gas when you heat them? So this is a general question for liquid and for gases. What happens? Here we have liquid water, okay, flowing at certain temperature, maybe 70 degrees Celsius, okay, maybe higher. So here what will happen? Here in this radiator it is open. Here we have like this grill here, okay, and open from both directions, from top and bottom. So here we have passage for gas, which allows the gas flowing smoothly inside this passages. So at the beginning, before gas start passing, we have stagnant air inside. So whenever we have a flow of water, then this gas start heated up. What will happen to this gas? What will happen to the particle of this gas when it heated up? Its density become less. So if we heat a gas and its density become less, then it will rise up, okay, and all of the gas actually would rise up, okay. So here we have empty space. What will happen to this empty space? A new quantity of air, which is colder, will come and occupy this place again, okay. Then it will heat up, so it will rise up. When the quantity of gas rise up, it will cool down. Once it's cooled down, it become heavier. When it's become heavier, it will go down, okay. Then it will come and occupy this place. It will heat up again. It will become lighter, raise up. Then it will become cooler, okay, become heavier. The particle become very close to each other, so it's become heavier. Then it will sink down, okay, and this process continue from this direction or from this direction, okay, in the same manner. Okay, so the particles spread out and become less dense when this happens, when we heat them, okay. So this is the answer. So whenever we heat the particles of liquid or gas, it will spread out, okay, and become less dense, so become lighter. So here it's at the beginning, this is the particle, okay, this is the distance between particles. Once we heat them up, the distance between particles become larger, and then it become denser, okay, it become lighter. See, so when the particle spread out, become lighter, okay. When the particles become closer, it become denser, okay, it become heavier. So cooler or more dense fluids sink through warmer, which is less dense fluid. True or false? True. So warmer liquids and gases rise up. Okay, cooler liquids and gases sink down. And actually, this process we call it natural convection. Natural convection. Why we call it natural convection? Because fluids will circulate based on the density change. Okay, based on the difference on their density. Okay, this is the reason of movement of the liquids. Once it touch a hot object, this is hot radiator or hot conductor, its temperature will vary. As a result, density will vary. So the movements start occurring due to density variation. And the natural convection, usually we call it buoyancy effect. It happens due to buoyancy effect. Why buoyancy? Because buoyancy actually depends on the density of the fluids. So as we mentioned, when the density become less, it will rise up. When the density become low, it will sink down. So it will sink through the warmer fluids. Okay. So هذه بتطفو للأعلى وهذه تغرق للأسفل اللي بتكون density higher. Okay. So this is density for hot fluids become lighter, and this density for cooler become heavier. Okay, so we call it buoyancy, and this is classified as natural convection. Of course, once we have natural convection, then we have forced convection. So this type is natural, and we have forced. Actually, we have third type, which is boiling or phase change. So when we can call the heat transfer happens through convection, when we can call it through conduction? Any ideas? Try to think about it for a while. Remember that we said conduction happens through metal, through solid objects. So this is the only condition required for conduction to happen. We'll have temperature difference, and then heat will transfer through solid. That's it. While in the convection, in order to call it convection, we need solid, okay, at certain temperature, and we need moving fluid at another temperature. Okay, moving fluid, it could be liquids or gas. So in order for convection to happen, we need conduction, because we need solid metal or solid medium plus moving fluid. Okay, then we can call it convection. Okay, together, both effect together, we call it convection. And this is very important, moving fluid. If it is not move, if it is stagnant, okay, then this is we can classify it as conduction. Okay, because stagnant, the same requirement for the conduction to happen, which happens through solid stagnant object. Radiation, the third type of heat transfer. How radiation happens? When we can call the heat transfer due to radiation. Any ideas? So the best example, as you can see from the figure below, is the sun radiation. Okay, أشعة الشمس توصل على الأرض. The heat transfer from sun to earth through radiation. So heat transfer by radiation is the transfer, we can define it as the transfer of heat through electromagnetic waves. Okay, so this happens due to photons or electromagnetic waves. So this electrons become more energetic and emit radiation in terms of thermal radiations. Okay, so this is happening due to electromagnetic waves. So here's the question: how does heat energy get from sun to earth? Is it due to conduction? Is it due to convection? Or it is due to radiation? But bear in your mind that the heat transfer from sun to earth how? Through electromagnetic waves. But do we have any medium between them? We know the space. There is no medium. Okay. So in conduction we need solid medium. In convection we need moving fluid plus solid. So let's assume that this is the solid, and here we don't have any medium. So the only answer, heat is a transfer only due to radiation. So there are no particles between sun and earth. We have space, no particles. So it cannot travel by conduction or by convection. So the answer is by pure radiation. Of course, in practical, we'll face the three types of heat transfer. We'll face conduction, convection, radiation. But here, in this example, we have a pure radiation. Thermodynamics, the previous part of this course, and the heat transfer. What is the relation? How we can differentiate between them? How we can define heat? Heat, the form of energy. So you can easily say that this is energy. Okay, that can be transferred from one system to another as a result of temperature difference. Okay, so this is the only requirement for heat. So heat is energy transferred due to temperature difference. That's it. Thermodynamics is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to another, as we saw earlier in the previous session. Whenever we are tackling a problem that involves heat, we don't care. And this is in thermodynamics. We don't care what is the source of heat. We just take a quantity, okay, from one equilibrium state to another, and that's it. But remember, when we are dealing with work, we have too many scenarios for work. We have too many equations. So we dig deeply with regarding work. But for heat, we take it as is. So in this part, we'll dig deeply to know from where this quantity of heat comes. Okay, is it Q due to conduction, or is it a Q due to convection? Okay, or is it the Q due to radiation? Okay, and for each one there is a relation. Okay, heat transfer deals with the determination of the rates of such energy transfer as well as variation of temperature. Okay, the transfer of energy as heat is always from higher temperature to lower temperature one. So please remember this rule. Always heat transfer from more energetic system or point to a lower energetic point. Okay. Heat transfer stops when two mediums reach the same temperature. Okay. Whenever delta T is equal to 0, then there is no temperature difference. That means there is not a heat transfer. Heat can be transferred in 3 different modes: radiation, convection, conduction. Okay, all modes of heat transfer require the existence of temperature difference, and this brings us to the initial definition, which is energy happens or energy transfer in terms of thermal as a result of temperature difference. Okay. Internal energy and enthalpy. Internal energy, we saw it earlier that this is U, and the enthalpy is H. And when we define the first law of thermodynamics, we take it as U and H without defining this H is equal what, and without knowing this U is equal to what. Okay, but we defined this, we saw it earlier. In the analysis of system that involves fluid flow means we have open system. Okay, we frequently encounter the combination of properties U and what we call this term. This is we call specific internal energy, but what about this one? We call it flow energy. So the combination is defined as enthalpy. It is one form of energy, but this energy for fluids that is in motion. Okay. The term BV represents the flow energy of the fluid, also called flow work. Okay, flow energy or flow work. So whenever we have a system that there is mass crossing the boundary in and out, then this energy we can define it in terms of H. Whenever we have a stationary system, then we call this energy stored in the system as, okay, here energy stored is H, here energy stored is U. The internal energy U represents the microscopic energy of non-flowing fluid, stationary fluid, and the enthalpy H represents the microscopic energy of flowing fluid. Specific heat of gases and liquids and solids. So specific heat, this is very important property, okay, which defines as the following. So it is the energy required to raise the temperature. So let me define it and in the same time refer to this unit. This is the unit of specific heat. So in the statement of the definition, it states that it is the energy, here is the energy, kilojoule or joule. Okay, so it is energy required to raise the temperature, of a unit mass, 1 kilogram, of a substance by 1 degree. So this is 1 degree. So if I refer back again to this definition, to this unit, so it is the amount of energy required to raise the temperature of a unit mass by 1 degree. Okay, so either we'll depend this unit actually. Okay, and you can see the specific heat in other units. Okay, but mainly we depend this one. So here is the definition. So if I ask you to calculate the specific heat, so it is amount of energy divided by amount of temperature raised divided by amount of mass. Okay, so 5 divided by 1, this is 5 kilojoule per kilogram Kelvin. This is the specific heat. There are two kinds of specific heat. We have a specific heat at a constant volume, and we give it subscript V, specific heat, and this is constant volume. And we have another type, specific heat at a constant pressure, CP. So either CV or CP. The specific heats of a substance in general depends on two independent properties such as temperature and the pressure. So this property, specific heat, depends mainly on pressure and temperature in general. But here we have a special case, first special case. At low pressures, all real gases approach ideal gas behavior, and therefore their specific heats depends on temperature only. Okay, so this is a special condition for a real gas. It will act as an ideal gas. When this happens, when we have very low pressure, then this value and this value depends mainly on the temperature. Okay, so here you can see that the air is behaved as an ideal gas. Okay, so here we have temperature variation, and here we have another temperature variation by 1 degree. So here is the CV 0.718, and here this is the new value for CV depending on temperature only. Now, what is the relation between internal energy U, enthalpy, and specific heat? Specific heats, as we mentioned, we have two types, CV and CB. So I'll take the last equation from each column. So here delta H, delta U. So delta U is a function of CV, and delta H is a function of CB. Okay? Of course, the unit of each term, delta H and delta U, is in joule or kilojoule. Okay? So delta U can be defined as mass multiplied by specific heat at a constant volume multiplied by delta T. Okay, and delta H the same, mass multiplied by CB, specific heat at a constant pressure multiplied by delta T. Why we take the average value? Because we have temperature variation, and the specific heat value will vary. Then usually we take the averaged value, and usually we drop this subscript averaged. Usually we drop it. You will see that in the coming equation that CB is written without adding average as a subscript. Another special case, when we have incompressible substance. Incompressible means density remain constant. So incompressible substance, it's defined as a substance whose specific heat or density does not change with the temperature or pressure. Then we can classify this as incompressible. The constant volume and constant pressure specific heat, constant volume CV specific heat and CB are identical for incompressible substance. So whenever we have incompressible substance, then we can say that CB equal CB. So they are identical. The specific heats of incompressible substances depend on temperature only again. Okay, so this is the second special case. And delta U, we can say it's equal to M C averaged without mentioning whether it's CB or CB because they are same, multiplied by delta T. So here if we have this substance, iron, which is incompressible, then we can say that CB equals CB equal constant value. Energy transfer. Now we'll start talking about equation of energy, but let's start with defining the units for each symbol. So if we are dealing with a Q, uppercase Q, then this is joule. If we are dealing with a Q dot lowercase, okay, but with dot, this is mass flux. Okay, so this is mass, or sorry, heat flux. Now, uh, if we are dealing with uppercase with dot, Q dot, this is heat transfer rate. And we saw this earlier in thermodynamics, but it's good to refresh your mind. Heat transfer rate. And its unit is joule per second, okay, or watt, okay. Now, in order to convert Q to Q dot, from Q dot to Q, just multiply it by delta T, so second with second cancel out, and we go back to joule. If we need to convert it to heat flux, then we'll divide by Q dot by area. So heat transfer rate, which is Q dot, is the amount of heat transfer per unit time. Heat flux, which is Q lowercase with dot, is the rate. This is the rate because it's watt per meter squared per unit area, normal to the direction of heat transfer. Power is the work done per unit time, and its unit is, its symbol is W dot, and its unit is watt, or joule per second. Okay. So energy can be transferred to or from a given mass by two mechanisms, either heat transfer and work. Okay. So here is two examples. This is a closed system, okay, but still energy can transfer from inside to outside because here we have temperature 80 and the surrounding temperature is 25. Then the temperature will transfer from inside to outside. Okay, here another example. We have a plane wall, okay, with certain area. So we can calculate the Q dot heat flux, rate of heat flux by dividing Q dot by area. Area is 2 multiplied by 3, and remember that we usually take the perpendicular area with the Q uh, as its transfer in this direction. Okay, so usually we take this area, perpendicular area. So if we are talking about this surface, then this is 2 multiplied by 3. So when Q is uniform over the area from each single point on this area. Okay. Here in this example, this is the sensible and latent forms of internal energy can be transferred as a result of temperature difference, and they are referred to as heat or thermal energy. Okay, here we have phase change. Okay, then we have sensible and latent as well. Okay, so it will transfer in terms of Q due to temperature difference. Okay, the first law of thermodynamics we saw it earlier in the thermodynamic part, or we call it conservation of energy principle. It states that energy can neither be created or destroyed, nor destroyed during a process. It can only change forms. And we define this equation. We said the total energy entering or crossing the boundary minus total energy leaving the boundary, or again crossing boundary to the outside, equal to the amount of energy stored, change in the total energy of the system. Okay, So delta E for a system, delta E out, delta E in. And each term is written uppercase, then their unit is in joule. So the net change, increase or decrease in the total energy of the system during the process is equal to the difference between the total energy entering and leaving. So this is the explanation of this rule. Or in terms of rate, this is rate of energy. So this is energy balance for any system undergoing any process in rate form. Okay, in rate form means uppercase with dot, uppercase letter with dot. Then this is joule per second or watt. Okay, and this term means amount of energy stored per unit time. Okay, amount of energy stored in the system per unit time. Rate of energy of a change in the internal kinetic potential, etc. Energies per unit time. Okay, so once we set rate means per unit time. Okay. So energy stored, we said earlier that it's due to either kinetic energy, potential energy, or internal energy. Okay, so usually we drop these two terms and we end up with U. If we have flowing fluid, then certain amount of B multiplied by V from work will come and combine with this one, okay, to form H intake. Okay. Okay. If we have a steady rate of energy transfer, then the last term in the previous equation, this one, will go to 0. If it is steady, means energy transfer at a steady rate. Okay, so steady means there is no variation with time. So if I derive energy with respect to time, then this term will go to 0. And we end up with energy in minus energy out equal to 0, or energy in equal energy out. Energy in could be due to heat, it could be due to work or mass. Okay, so energy in terms of heat, work, and mass, and energy out the same. Could be heat, work, or mass. In heat transfer problems, it's convenient to write heat balance. So we use to write Q minus W equal delta E. This is the first law of thermodynamics, delta E. Okay, we used to write this equation. But now, once we are caring a lot about this value, so we need to modify this equation a little bit. So in heat transfer problem, it's convenient to write heat balance and to treat conversions of a nuclear, mechanical, chemical, electrical energies into thermal energy as heat generation. So we'll write Q, instead of writing this Q, we'll write Qn minus Q out in this form, okay, plus E dot generation equal delta E stored in the system, okay. This E generated, it could be due to electrical, could be due to mechanical, as we saw earlier in the previous part, thermodynamic part, or it could be due to chemical, and or due to nuclear. Okay, of course, usually we don't have the problem that we are dealing with the nuclear, we don't have chemical, we don't have electrical. Okay, so we end up with mechanical. So anything related to this type of energies combined together, and we insert it in this equation as E generated. Okay, so anything happens due to temperature change, this is a Q. Okay, anything else is due to energy generated. Okay, example of energy generated. For example, here, this system. Do we have inside it electrical wire? Do we have inside it chemical reaction? Okay, and here we have source of heat inside this boundary. Okay, this is the boundary. Now, if we have here electrical wire outside, then this term is equal to 0 if the source of work is outside, electrical or chemical or nuclear. If it is inside the boundary, if E generated due to nuclear, chemical, mechanical inside the boundary, then we can substitute value. If it is E generated outside, then inside the system we have no generation, then this is 0. Then anything produced from outside will enter this system in terms of temperature or in terms of Q. Okay. So شرط تعويض هذه الترم بهذا القانون إنه يكون عندي هذه الفورمز of energy inside the boundary. Okay. If it is inside, we can substitute it with a certain value. If it is outside, we'll substitute it 0. Okay. Okay. Energy balance for a closed system. So let us see the scan. And inside the scan, we have certain mass. Once it is closed, then we have this property, specific heat equal to CV. Initial temperature T1, طبعا this CV averaged. Okay. And here final temperature T2. So if I need to calculate Q transferred to the surrounding or from surrounding to inside, okay, we can say that Q equal mCV T1 minus T2. Okay, simply. But from where we calculate this amount? Do we have any equation that prove this result? Okay, so this is the result. This is final form of this equation. Q equal m CV T1 minus T2. If I need a dot, then I write here and dot. So if we have a closed system consisting of a fixed mass, the total energy for most systems encountered in practice consists of internal energy, U. Okay, so this is the energy stored in the system. Because we have a closed system, then whenever we write Q minus W, we must write here instead of delta E, delta U. Usually we ignore kinetic potential. Now here inside this can we have no work. Okay, so this is go to 0. And instead of delta U, remember we write M CV T2 minus T1. Okay, so this is the proof of from where we got the value of Q. Okay. This is especially the case for stationary systems since they do not involve any change in their velocity or elevation, so there is no kinetic or potential energy. As a result, we benefit from the first law. Okay, we can write it in this form. Still, we can benefit from this form, not necessarily the previous form, or we can use it. So you can say Qn minus Q out, okay, plus delta generation or E generated equal delta U. Okay, still you can use both. So do we have any generation inside it? Do we have chemical reaction here? Do we have a nuclear? Do we have chemical? Do we have mechanical? Do we have electrical? Nothing. Okay, so this will go to 0. Do we have a Qn? We don't have a Qn, we have only Q out with minus sign, and instead of delta U I can write mCV delta T. Now energy balance for a steady flow system. Steady flow system means we have open system. Okay, open system. So what do you think Q will equal to what now? If I substitute Q minus W equal delta E. Instead of delta E I can write delta H, and delta H equal to M CB delta T. Okay, and work here equal to 0. Then, since we don't have work, then Q will equal mCB delta T. This is the final result of this slide, but will be detailed. So a large number of engineering devices. So most of the engineering devices we have flow in, flow out. Okay, such as water heaters. Okay, car radiators involve mass flow in and out of a system. So those are applications. We have flow, we have heat, we have thermodynamics. So we have 3 parts, and are modeled as control volumes. So why we set control volume? Because the boundary, the control surface inside it, we have here mass in, mass out. Inside it, we call it, the volume is controlled, not the mass controlled, because this is open system. Most control volumes are analyzed under steady operation. So usually we assume that the variation with time is steady in terms of temperature. The term steady means no change with time at a specified location. And here is the problem. This is open system, mass flow in, mass flow out. Okay, so mass flow rate, which is m dot, this is the symbol of mass flow rate, is the amount of mass flowing through a cross section per unit time. So its unit is kilogram per second. Amount of mass per unit time. Another term we'll use it here, or another parameter, is the volume flow rate. And volume flow rate will use this symbol, V dot. Okay, it is the volume of a fluid flowing per unit time, inside pipe or inside duct. So it is meter cube per second. And I think you know the difference between pipe and duct. So pipe, we are talking about circular cross section. Duct, we are talking about rectangular or square cross section. Or simply, duct means non-circular cross section. Now, if I need m dot for mass n, m dot n, mass out, we should calculate from here. Rho multiplied by velocity multiplied by area. Okay, or simply would write rho multiplied by v dot. Okay, instead of velocity multiplied by area, I can substitute volumetric flow rate or volume flow rate, which is equal velocity multiplied by area. So if I want to relate this equation together, I can write m dot v dot equal m dot divided by rho. Now, if I care about q dot, then q dot here will equal m dot delta h or m dot cb delta t. So remember, when we start with talking about q minus w equal delta e, and delta e for this system is equal to delta h, and work here is equal to 0, and this delta h is equal to m if we are dealing with dot. Okay, so this delta h means this is dot, sorry. So this is what? Okay, so this is with dot, then m dot delta h, and this is equal to m dot cb delta t. Okay, actually this equation is represented here. Okay, so here it is, delta h in lowercase, this is cv delta t, and delta u in lowercase specific, this is cv delta t. If I need it in uppercase, then simply multiply this term by m, then it becomes uppercase, and this multiplied by m, this become uppercase. And this is kilojoule per second. So this is the same example here, mass in, mass out. Okay, and here we have control volume. This is control surface. Okay, so the mass flow rate of a fluid across section is equal to the product of the fluid density, average velocity, and the cross sectional area. So it is rho multiplied by V multiplied by A. So if here we have mass in, mass out, okay, so the amount of Q entering to the system is equal to delta H, amount of temperature change. So here it's entered as T1 and it exits as T2. So the amount of energy transfer is equal to Q dot. Under steady condition, of course, we'll use this assumption a lot. Steady condition, the net rate of energy transfer to a fluid in a control volume is equal to the rate of increasing in the energy of fluid stream flowing through the control volume, which is this part. I'll stop here after this slide. So next lecture, I'll start with this slide. Till then, stay safe and see you.